Started.
Yes, sir, now it started.
Yeah. All right. So if you have any question in sequence and series, so sequence and series will play a very important role in mathematics. So whatever you do, there will be sequences and series of functions, and one need to look at convergence stuff all the time. And those who will opt for mathematics, and they have to, of course, they have to, in any case, use, I mean, this sequence and series every day. All right. So if you have any question, this is time to ask. Anyway, today is what date? Second. So let us see an example of a series. Consider the following series: summation x squared by 1 plus x squared whole to the power n, n from 0 to infinity. All right. Does this series converges?
Yes.
Yeah. So what is the limit? So the series converges absolutely.
Sir, what is domain?
I mean, for a series, there is no domain unless it converges. So the point is where it converges. That will give you a domain of a function, right? So the series is not a function all the time. It's a series. It can be formal series. The sum may be infinity, may not exist. All right. So what you need is the series to be convergent to say this is a function. All right.
Yes, sir.
Okay. So the series, firstly, the series converges pointwise, right? Now, what is the limit? So you see here a geometric series, right? So at x equal to 0, the series x squared by 1 plus x square root to the power n gives you 0 at x equal to 0. All right. And for x not equal to 0, you have this x squared summation n from 0 to infinity 1 by 1 plus x squared, right, to the power n. And this is a geometric series. So this is a geometric series. convergent, actually convergent because this modulus is always less than 1, right? Maybe I should write it also. Mod of 1 by 1 plus x squared is always less than 1, and plus the series, the series 1 is a convergent geometric series, right? Is it clear? Is it clear?
Yes, sir.
Therefore, for x not equal to 0, we have the limit. The limit is, or the value of the series is x square into 1 by 1 minus 1 over 1 plus x square, which gives you 1 plus x square. So see the importance of geometric series. So most of interesting exercises or examples are constructed using geometric series. All right. So now another question which we have answered last time. So when does a geometric series summation x to the power n from 0 to infinity converges absolutely, uniformly, pointwise? Right? So we have done this last time, right? Isn't it? Maybe I should put this question in red. Yeah, can anybody answer this?
Sir, if x is mod x is less than 1, then pointwise convergence is provable.
Right. So pointwise mod x less than 1. Right. Absolutely.
That will also be at mod x less than 1.
Hmm. All right. So is it clear?
Sir, can we say that if the sequence of this series converges to some sequence which is less than 1 by n, then it will
No.
converge pointwise. This series
Sequence
will
of,
converge.
what is sequence of series? Sequence of partial sums.
Not sequence of partial sum, but sequence xn. Fnx is equal to xn. X raised to
Eh,
power n.
That converges implies series converges. Is it true?
Uh, we know that one by, if uh, some sequence is smaller than 1 by n, then it will converge. Its series will converge.
You know, any series which is less than 1 over n converges. Any series whose terms are less than 1 over n converges. Do you know that? Can you prove it?
Okay, well, I will try.
Yeah, so you try and let me know, okay? In this case, this is very simple. So to show this converges pointwise, it's actually the same as showing absolutely. So showing absolutely is the real geometric series, right? So absolute means summation mod x to the power n, right? You put n equal to 0 to k, or you just yeah. So you put k equal to 0 to n, rather k equal to 0 to n, and this is k. And now this, you know, where it converges, right? Right. So what is the sum?
One upon one minus x into. Oh no, it's not till infinity.
No, this finite sum. What is the finite sum?
It's just mod x to the power, or 1 minus mod x to the power n plus 1 divided by 1 minus mod x.
Right. True. Right. 1 minus mod x. Right. So when mod x less than 1, mod x strictly less than 1 implies mod x to the power n plus 1 converges to 0 as n tends to infinity. So therefore, this sum 1 plus x, 1 minus x to the power n plus 1 by 1 minus mod x converges to 1 minus mod x. Alright? As n tends to infinity. Hence, the series summation x to the power n from 0 to infinity converges pointwise on mod x less than 1, right? Now, what about uniform convergence?
So mod x less than 1 minus delta for positive delta.
Right. So you need a compact set. So this is now an open set. So mod x less than 1, this gives you an open set. Minus 1 to 1. Now you need a compact set because
Because otherwise the supremum would be equal to 1, and so the summation of 1 doesn't converge.
no. That doesn't prove that it converges for mod x less than 1 minus delta.
No, I mean if we take 1 minus delta, then the supremum of it is, I mean mn, the value of mn is 1 minus delta. So that
Right. Minus
always,
delta? No. Yeah, 1 over 1 minus delta. No.
yes, so that
Hello?
converges because 1 minus delta lies between 0 and 1, strictly between 0 and 1. So it's a
Right.
convergence.
Right. Right. So now consider mod x less than 1 minus less than equal to 1 minus delta, delta greater than 0. Delta belongs to 0 and 1. Right here. So this implies mod of x to the power n lesser equal to 1 minus delta to the power n, right? Now
Yes.
you use Mn test. Right, so the or it's called comparison test also. It's comparison test. So this series is dominated by this series. This summation x to the power n is dominated by 1 minus delta power n. Now this series converges by a comparison test. This series converges uniformly on not x less or equal to 1 minus delta. Now this
So,
absolutely, yes.
so comparison test doesn't directly tell us about uniform convergence, right? It's only because from the 1 minus delta raised to n series, we can pick an n naught which is not dependent on x, that we infer that convergence is uniform.
No, what is the statement?
Sorry?
What is the statement of this comparison test?
Uh, if yn greater than xn converges, then so does xn. Like if the
No,
series.
so we have stated an Mn test using, so what I called a comparison test here, which is also called Weierstrass Mn test. Mn test, which is the same, which is if f
Oh, okay. Sorry.
Fn is a series and mod of Fn is bounded by the some number Mn and summation Mn converges, then this series converges uniformly.
Okay. I confused it with another comparison. Sorry.
Yeah, I mean, this is the most general. I mean, if you look at the functions and uniform convergence, uh, well, not most general, but yeah, this most used one. So this converges uniformly on this one. All right. So actually, on every compact subset of 0, 1, actually, on every compact subset of minus 1 to 1, the series converges uniformly. Actually, we have shown more. We have shown it converges absolutely and uniformly too. Right?
Sir,
Yes.
can't we say the same about open subsets of minus 1 comma 1?
No, because open up minus 1 to 1 is also an open set.
No, I'm not talking about minus 1 to 1, but a strict open subset of minus 1 to 1.
Then you just make it close it up. Even strict subset, it is not true. For example, this delta comma 1, this set on this, the series does not converge uniformly.
Yes, I mean if the endpoints are open, then the series does not converge.
Yeah, no endpoints. Yeah, if you go up to 1 or minus 1, then series does not converge. Otherwise, it will converge. Otherwise, you can make closer and it will be a compact set inside 0, 1, inside minus 1 to 1. All right.
Yes, sir.
Okay, series does not converge uniformly. uniformly. All right. Yeah, any other question? So this is the most important series in your life, and if you are in science. Okay. So if you have any question here, and mostly the other things, other series that is constructed for usually, which is simple, those are constructed using geometric series. Just like the example here, right? So uniformly, here we have this one. Now let's look at this original series. Yeah, any question? Anybody?
Sir,
Yes.
in the uniform convergence, like where is the compactness used actually?
Because you see here in the MN test, it's bounded. So you are actually putting the endpoint,
Yes, sir.
right? So this series increases. When you look at the interval 0 to 1, series increases. So so this series actually increases as mod x goes towards 1. All right. Now this one actually at the this one is the end point of the interval. So therefore you can bound it. So each of the member increases. So the series also increases. Therefore you can bound the series by this. Bound each term by this. That is possible because this here 1 minus delta is strictly less than 1. Otherwise it will be less or equal to 1. And there you cannot do any comparison. Right?
Yes, sir. Got it, sir.
Okay. So here it is this compact thing used. Yeah, any other question? So let's go back to this original example. So now this one, this series, now go back to the original. Let us go back. Original example. So you have summation x power x square by 1 plus x square to the power n equal to 0 to infinity. All right. Now the question where does the series converge uniformly, right? And absolutely also, right? So pointwise we have seen it. Pointwise it converges everywhere. So and pointwise, and for pointwise we have seen everywhere, which means on the whole of R. Absolutely.
That will also be on whole of R, I think.
Right. So you see here 1 over 1 plus x square. This is already positive. right? This is already series of positive terms. So mod of this is always mod of this one is this itself. Right? So therefore the series converges absolutely on whole of R. Alright. Now the main question is, where does this converge uniformly?
Will it be minus a comma a closed interval where a is any real number?
No.
Open interval. Oh no.
You have to get rid of the 0 as well, I think.
Yeah, that is true. So the problem is, you see here the limit. What was the limit? The limit was this, at x equal to 0 and x not equal to 0, this one. So we need to look at the limit. So pointwise limit is very helpful in understanding the convergence, whether it converges uniformly or not. The limit. So which means this. So define, since it converges pointwise, we can define a function. Define fx to be summation n 0 to infinity x square by 1 plus x square power n. So now this fx will be, define fx like this series. So fx will be 0 at x equal to 0, and this will be 1 plus x square at x not equal to 0. So you clearly see f is not continuous at 0, right? Clearly f is not continuous at x equal to 0, right? Yeah. What happened? This is simple, right?
Yes sir. Yes sir.
Yeah. Yeah, this is simple. As x tends to 0, this goes to 1, but it is 0 here. So this is not continuous. So if it converges uniformly around 0 also, then the limit would have been continuous by a theorem that we have proved few class back. All right? Yeah. So the problem, the point.
So can you explain in terms of there being an n naught for all x, why it fails at x is equal to 0?
Yeah, but I don't have time. So that would be easy, because you see, it will fail at 0. So what you will do is, I'll just let me give an argument, a brief sketch. So you will choose a point nearby. So this is the function f. This is the function f, the limit, right? Now you want to choose. So this summation. So first you tell me this one, sum fn. So this is a general thing. N from 0 to infinity does not converge uniformly. Right? So this one, what does it mean? Yeah. What does it mean?
It means that the sequence of partial sums don't converge uniformly, which is to say that there is no one natural number such that for
No. There is no one natural number. This may be okay to think, but it is not a mathematical term. All right. So you should give this. So this means you define Snx, which is summation j k equal to 0 to n minus 1 fnx. This series, which means this series Snx, Sn does not converge uniformly,
yes, sir.
which means there exists epsilon greater than 0 such that, tell me,
Such that the nth partial sum is greater than epsilon given some
what?
value of x.
For all natural numbers, there exists another small natural number,
Right. For all n, there exists
a certain particular n naught belonging to
n
natural
naught
number, and x belonging to the domain of the
and x
Sn,
belongs, let's say,
such that
yeah,
such that Sn of x minus the pointwise limit f, or any f for that matter,
right, fn, f capital N naught
of
minus
yeah.
f, no, it, see here,
In the at the very beginning, you should have a for all f, like any function. There is no function such that this
what?
holds.
What? So this Sn does not converge uniformly. What does it mean?
So such that mod of Sn minus the limit, like the pointwise limit at that point. Uh, the function that you've created from the pointwise limits. It's enough
Right.
if you shoot for that one function, because
So it does not converge uniformly to, let's say, S.
okay.
Okay,
Then Sn of x,
Sn of
S
x.
n naught, yeah, of x
Mm-hmm.
minus minus s of x greater than epsilon.
Mm-hmm. Greater than epsilon, right?
That's it. Yeah.
So what is the role of this n, small n and capital N naught?
So for any natural number, if we okay, that's what you meant. N naught should be greater than no. Uh, N naught is greater than small n. Yeah. Capital N naught is greater than small n.
Mm. Right. There exists. See here. Yeah.
It's, it works for all natural numbers. And we shouldn't
What?
have an n naught.
This is the
No,
formal like negation of the statement of convergence.
no. This is no. It does not. But you said. See here. It does not converge pointwise. As you are saying, right?
No. This is just the formal negation of the statement of.
I think for not converging uniformly, we should say that for all epsilon, there exists an x such that
This is fine. This is
No, I
not get.
think generally what we have in the convergence is that for all epsilon greater than 0, there exists an n naught belongs to natural number, such that for all small n greater than n naught, the difference is less than epsilon. So the formal negation should be there exists a positive epsilon such that for all natural numbers, we don't
Yeah.
need to use n naught. For all natural numbers, and there exists an x belongs to the interval E or the set E such that s of small nx minus s of x is greater than epsilon. And it should happen for all natural numbers because the existence of
So
is not
what is the pointwise negation of pointwise convergence?
I mean, that is what I think is the negation of pointwise convergence.
No, we need negation of uniform convergence, right? We
Yes.
need the negation of uniform convergence. So this for all n, there exists n naught and x depends on n naught, or depends on n rather.
So can you please explain why we need the N naught criteria?
Oh, that doesn't matter actually. Here you see here. So what is the so see here n naught greater than n, it comes as formal negation of for all n greater than n naught, right? So instead of for all, you say this here for each n. Well, you can put small n, right? But small n, if you put small n for all n, you have Sn x minus Sx. But that may not be true, right? That Sn minus Sx may not, may not be greater than epsilon, but it might be, there might be some other different one which is greater than epsilon. So for each n, for all n, so the point is here, suppose this is small n. At this point, you have differences Sn minus S, right? Whatever x is, you can get an x. Now the point is, at this point, this may not be greater than epsilon, but somebody else. So what we had? We had this in uniform convergence. In the definition of uniform convergence, we had what? For every epsilon greater than 0, there exists n naught n such that Sn minus S, of course, this is x less than epsilon for all n greater than n naught and for all x in E, right? Now see here. Now if you want to change to negation, this will become there exist. This will become for all. Now this one. So look at this inequality. Look at this inequality. This part. This part is true for all n greater than n naught. What is the negation of it? There exists n naught such that greater than n. Here, look at this negation of this one. For all n bigger than n naught, this is less than epsilon. So what is the negation? Negation is there exists a small n greater than n naught such that this one greater than epsilon. Right? Is this clear? And that's why you get this n naught here. You get n naught here instead of just n. Is this clear?
Yes, sir.
All right. So this is the negation of this is what it means to say does not converge uniformly. Now you see here you need to find that x. So the x you will take is a point near to 0. So in our example, we take a point near the origin, near to 0. All right, not exactly 0, but 0, near 0. And there you will see this Sn minus Sx. Of course, yeah, not this one, of course. Well, it depends on n naught. So you go with the so you will generally take what? You will take x to be 1 over n. So take a point near 0. In fact, not a point actually. Depend. You take the points x to be 1 over n, right? And at each 1 over n, you will evaluate. And you see this will happen. You see for each n, we look at this 1 over n, right? And as you go near 0 and you'll see what happens to Sx and x equal to 0. So those are the points you will take. 1 over n would actually give you this mod of Sn naught. And you can just start with Sn naught 1 over n naught minus Sn S of 1 over n, 1 over n naught, and go with that. And this is geometric series, so you can actually calculate also. So this part of calculation you need to do yourself. And the point you take is 1 over n. Generally it will work here. All right. So I would have done it with I would have time, but this is a calculation which you need to show here. This which you need to look at the sum, the geometric sum of the geometric series, which you know already. Okay. And putting the value 1 over n. All right. Yeah, does this clear? Is it clear with you? Or you have still you have trouble in understanding?
Yes, sir, it's clear.
Yeah, so do this, I mean, this computation, computations takes time, and this is not for class, actually. So, yeah, so there will be a tutorial today also, and they will explain about this assignments. Yeah, any question here? So maybe let me give you an exercise. This will be part of next assignment. So if Fn converges to F uniformly, Gn converges to G uniformly, then show that Fn plus Gn converges to F plus G uniformly. is or does Fn times Gn also converge to Fg? So here, does it converges? If it converges, then give a proof, and if not, give a counterexample, and maybe discuss situations where it converges. Yeah, any question?
Sir, I think we had this question in the first assignment itself.
Oh, it was there?
Yeah, question 2 was the first part, and question 3 was the counterexample, I guess.
Oh, okay, okay. Then it's fine. I thought, yeah, I don't remember it. Yeah, then this is fine. This is already done. So this is done. Fine. So yeah, so then let me give you another one. I don't know whether I've given that one true, because the first assignment was actually a lot of exercises was there. So fx, no, I don't think it. I have given it 1 plus n square x in from 0 to 1 to 1 to infinity. So this is, consider this series. Consider this series. Discuss where the series converges pointwise uniformly, absolutely. Okay. Yeah, any other question?
So, will the tutorial be in this link or with some other meeting?
Yeah, it should be in this link. I told them that this is a link. You will they will do this one, but from next time onward, we will make 3 groups. Okay.
Okay, sir.
As shown last time, the 3 groups already divided last semester. So the same group, the groups will be the same. And next time there will be there are 3 tutors, so they will take one each of the link. They'll go in each one of them. All right. So if you have any other question, let me stop this broadcasting. Any question? And very few attendance, isn't it? What happens to others? Uh, Anyway, that is fine. So so you don't have any other question, okay? All right then. So we'll meet again tomorrow. Okay. So tutor should come.